Hello everyone, welcome back. So today we're learning how to graph functions using derivatives. So our goals is to be able to use the first and second derivatives to find things such as critical points, places where the function is increasing, decreasing, where what kind of concavity you have, where it changes, local and both absolute maximum, minimum values, and also inflection points. And then also use those things from calculus and also some other techniques you learn from algebra to be able to graph a function. And once again, this is good. This is useful for helping to better understand how you can use algebra and calculus. And also, this is basically the way people before computers and calculators, the way people had to graph functions, especially complicated functions. So here's a guide to graphing functions. This is actually taken from a textbook. So I just, instead of rewriting all these things, there's no need to. And basically kind of talk through them, and then we'll do a few examples, a couple examples. All right, so for some function, so what you want to do is first off identify the domain or interval of interest. Your domain may be all real numbers, or could be part of that, could be some specific domain, maybe between two endpoints. Whatever it is, make sure you have your domain. Also take advantage of symmetry. So we're talking about even and odd functions. There's symmetries there often we can use that make our life easier. For example, we know we have if it's symmetric about the y-axis, for example, then it looks the same on both sides. Of course, we're going to find our first and second derivatives. That's going to allow us to find critical values, places where you could have inflection points. Also, it tells us about our concavity and places where it's increasing and decreasing. That will help us to better understand the function. And once you can find the critical values and possible inflection points, you can also use first and second derivative tests for that if you like. Find variables which the function is increasing and decreasing, where it's concave up and down. Then also identify those extreme values, inflection points, local minimums, and if you're on a specific interval within points, absolute maximum, minimum values. Also, make sure you locate any asymptotes if you have an end behavior. So if you have any vertical asymptotes where the function is the denominator is 0, or the end behavior, what happens is the function goes toward infinity or negative infinity. So think about those kind of limits. I also find intercepts. That's more of a just algebra technique to make sure you can do that. And then kind of choose appropriate way to graph it. Have an appropriate window, appropriate range, and graph it with. So let's take a look at a couple examples. So first, and I'll just say our directions be to graph the function. Okay, so number one, let's say we have this. Our function, our f of x, is equal to, actually, I need to double check something for a moment. Make sure we're doing the right thing. Yes. Okay. Yeah, so first is going to be x cubed minus 3x squared. Now, of course, we can actually go to Desmos or graphing calculator to find what this looks like, but let's actually save that till the end to see how we did. Okay, so that's our function. Now here, so let's kind of step through these. Number one, this is what we call this number one. So our first step, or one of the first steps, these are our particular order, but let's find our domain. So here, there are no restrictions on our domain. Remember, this is a polynomial, so our domain is just going to be all real numbers, or negative infinity to infinity. Now, we're not going to try and graph it that way, obviously, but just that's going to be our domain. And once again, if you had a restricted domain, maybe you might say like between 0 and 5 or something like that. So if that's the case, make sure to take that into account and also be able to find the function at the endpoints. Okay, that's our domain. Now, here, what kind of symmetry it has is not as clear. So I'm not going to worry about the symmetry now, but that's something obvious. You can always determine whether it's even or odd function. We're not going to do that just yet. So next, let's actually find our derivatives. That way we can find out critical values, inflection points, where it's concavity, and those sorts of things. So f prime of x is, take the derivative of this. First part is 3x squared. Then minus is going to be 6x. That's our first derivative. And actually, let's kind of split this, and let's do our second derivative over here. All right, so our second derivative, that'd be 2 times 3, which is 6x, minus 6. And we're doing that because where our derivatives are 0 can tell us important things, okay? So On this one, let's find our critical values, or critical points. And remember, that's where you set the first derivative equal to 0. So 3x squared minus 6x is equal to 0. And this one, the best just to factor. It's a factor out of 3x. And what's left is going to be x minus 2. Set each factor equal to 0. And so our critical values for this one are going to be x equals 0 and x equals 2. So those are our critical values. The places where the derivative is 0. This could be local maximums or minimums or neither, but those are critical values. Okay. Now, here, let's find the possible inflection points. Okay. So that's where we're going to set our second derivative equal to 0. All right. And so it's going to be 6x equals 6, positive 6, or x equals 1. And once again, that's a possible inflection point. We don't know for sure if it is yet or not, but a good chance it is, because inflection points are often places where the second derivative is equal to 0. Okay, so what we can do, let's use our critical values to kind of help us find out what's going on with our function. Okay, so we have two critical values. So let's actually do, in this case, let's actually do the first derivative test. Tell us something about where the function is increasing, decreasing, all that. So that's a further step. And also get an idea of whether these critical values are maximum and minimums or neither. So the first derivative test, and what we're going to do is we're actually going to have our I'm trying to decide how long. I don't have a whole lot of space left, so I'll actually erase that for now. Okay, so we're going to have our two critical values, which are 0 and 2. So x equals 0, x equals 2, and that's going to divide our function essentially into 3 regions. Okay. Now, what we want to do is take our first derivative. And our first derivative, we can actually factor it this way. Okay, notice it's factored to 3x times x minus 2. What I do then is actually let's write down our factors of that. So 3x in this region, x minus 2, and then this is going to tell us the sign of f prime of x. Okay, so if you've seen the first derivative test before. So basically here we know our first derivative is 0 at 0 and at 2. Okay, so let's think about let's pick some test points in these regions. All right, so here just pick 1. And here's also, sorry, negative 1. Let's pick 1. And here just pick 3. Pick something simple. What we want to do then is think about plugging these in, and all we care about is what the sign of each factor is. Okay, so if you plug in negative 1 for x, that's going to be 3 times negative 1, which is negative. Okay, you plug in positive 1 for x, that's going to make this positive. That's going to be a positive here between 0 and 2 for this factor, this part of it. And then over here at 3, of course, plug in 3 for x, it's going to be positive again. You know, so it changes sign, or that factor changed sign. Right here, 0, because that was its critical value came from that. That's where it changed sign. And here for x minus 2, same thing. I plug in negative 1 for x, that's going to be negative. I plug in positive 1 for x, that will still be negative. If I plug in 3 for x, that becomes positive, and it changed sign right here at the one it was related to. Okay? So remember, we combine these. We have a negative and a negative is a positive. It's opposite signs. Positive and negative gives us a negative. Your two positive gives us a positive. And so what this tells us right here, this is where the function is increasing. This is where it's decreasing, and it's increasing here. All right, so what does that tell us then? That tells us that function here is x equals 0 goes from increasing to decreasing. Also known as continuous, and the derivative is continuous. Let's actually back up a second. So this, of course, is a polynomial. It's continuous everywhere. The first derivative is also a polynomial. It's continuous everywhere. The second derivative is also a polynomial. So it's continuous everywhere. So don't have to worry about holes in the graph or asymptotes, anything like that here. Okay, so The function goes from increasing to decreasing. So that means we have a local maximum value at x equals 0. And then it goes from decreasing to increasing. That means we have a local minimum at x equals 2. Okay, good. So that's the first derivative test told us those things. Now, we know some things where it's increasing and decreasing. Now, let's actually do the second, let's use the second derivative test, which will in part tell us the same thing. So we don't really need to find out whether these are local maximums or minimums, though it can confirm what we already found out. But also, we can use this then to help us find out concavity. Okay, so remember here, the second derivative, it's 0 at 1. And so that's where it can change concavity. So this is 1, x equals 1. And here, we only have essentially one factor. Everything is a factor, so you just have 6x minus 6. Okay, so in the same way, let's pick a value from this region. Let's pick 0 for here and just 2 for here. Once again, pick something that's simple. We're going to plug these in, and this can tell us then what the sign of f double prime of x is. Okay. Now, ordinarily, we also would plug in our, which actually these are also our critical values as well. We could plug in our critical values and tell us whether local maximums, minimums. We know that anyway. But let's plug these in. So if I plug in a 0 here, that's going to become 0 minus 6. That's going to be negative. Okay. I plug in 2 here, positive 2. That's going to make it 12 minus 6, which is positive. Okay. So here, that's the sign is negative and positive. So I only have essentially one factor. So the sign of f double prime is negative here and positive here. Okay. Remember, this is concavity. So basically, if it's here, this is concave down. Okay. Or opens down. This is where it's positive, it's concave up. Okay, good. And then right here so what tells us, since the concavity changes, so x equals 1, say since, and also the second derivative test tells us that if this is a critical value right here at 0 and it's concave down, this is a local maximum, which is what we found in the first derivative test. And since it's concave up, at this critical value, that's a local minimum. Of course, we already know that. But also, since f double prime of 1 is equal to 0, where the concavity changes, or more specifically, we already know that, but since concavity changes there, that's actually more precise. At x equals 1, x equals 1 is an inflection point. Okay, so x equals 1 is an inflection point. Okay, good. So now we know something about the calculus that tells us some things about the function. Okay. Now, next thing, so we identified our extreme values and inflection points. So this one also, let's think about in behavior. We said, of course, it's a polynomial, so no asymptotes. Okay. Now, as far as end behavior, what happens is we go far from 0. So remember our function. Let's write our function down again. So our function is f of x is equal to x cubed minus 3x squared. Okay. Now, remember, of course, this is an odd degree polynomial. It's the third degree. And remember, the behavior, the end behavior, far from 0, this looks like y equals x cubed. Okay. And so remember what's going to happen then when x is positive and really large, it goes to infinity. when x is negative and really large, absolute value, and negative, it goes to negative infinity. So, think about the limit. So the limit as x goes to infinity of f of x is infinity. Not infinity, I said it, but wrote 0. And then if we go the other way, the limit as x goes to negative infinity of f of x is equal to negative infinity. Okay. Now, the last thing you have to do is find the intercepts. And let me do that right here. So intercepts. All right, so once again, let's write our function down again. F of x is equal to x cubed minus 3x squared. Okay, if we factor this, take out an x squared, we're left with an x minus 3. Okay, now let's think about this. So an x-intercept, your x-intercept or intercepts, that's where y is 0. So if we set this equal to 0 and solve, x squared times x minus 3 is 0. Then we've seen this kind of thing before, to set each factor equal to 0, x squared is equal to 0, x minus 3 is equal to 0. Okay, of course here x squared, we take the square root of both sides, that's just going to be 0. That equates plus or minus the square root of 0, but then that's just 0. And over here, x is equal to 3. Okay, so our x-intercepts, we have 2 in this case. One is 0, 0, and the other is 0, 3, or 3, 0, rather. And then the y-intercept, you can only have one y-intercept for a function. That's the easiest one. Just plug in f of 0. And actually, that's just going to be, see right here, that's just going to be 0, because in factored form, you're putting a 0 right here, makes the whole thing 0. 0 times 0, 0 times anything is 0. And so the y-intercept and the coordinates are 0, 0. Okay? And actually, one more thing we should do is our local maximum and minimum. Now, we know our local maximum that is at x equals, I think it's x equals 0. Go back and double check. Yeah, 0 and 2. Local maximum at 0 and local minimum at 2. Okay, and so if we do f of 0, we've already done that. That's just going to be 0. So that coordinate is going to be 1, 0. Okay, now our local minimum is at x equals 2. We plug in 2. Now this one, I have to do a little bit more work. So I can use either form, this form or that form. So it'd be x squared, x cubed minus 3x squared. So we'll do 2. So 2 cubed minus 3 times 2 squared. And so that's going to be 8 minus 3 times 2 squared. That's going to be 2 squared, of course, is 4 times 3 is 12. That's going to be negative 4. And so that value, then, that coordinate is going to be 2, negative 4. Okay, now let's put all this together. So several points. Let's think about it. So we have a y-intercept at 0, 0, and also an x-intercept. When our x-intercept is there, x-intercepts at 3, 0. So let's start to graph this. So this is the main thing I want to get out of this. It's the graph, a basic graph. Okay, so we know we have a point here, important point, 0, 0. It's one of our x-intercepts. And also here at 3, 0. Okay, now we also know that we have a local maximum at 1, 0. Oh, 1 0 0 0. Sorry about that. 0 0. Okay. And another one at 2 negative 4. So 2 negative 4 is going to be right about here. Okay. So we have intercept here. It's also local maximum. And also we have inflection point. And I actually forgot to actually write what our inflection point was going to be. I can actually kind of squeeze that in here. So inflection point. That was at 1. If we plug in 1, so f of 1 is be 1 cubed minus 3 times 1 squared. And that's just going to be minus 1 to minus 3 is minus 2. And so that's going to be 1 negative 2. That's our inflection point. 1 negative 2. Be right about here. Okay, so if we graph this, so then this is a maximum, this is a minimum. So something, actually don't need that little curve there. Try that again. All right. Look something. Now remember also it's going to go negative infinity in this direction, positive infinity in the other direction. Look something then like this. And I missed that point, but you get the idea. So I'll rearrange it here. And this should be smooth. I'll draw the best, but you get the idea. Okay. So 1 negative 2. Our graph should look something like this. So this is f of x equals x cubed minus 3x squared. Okay, that's our graph. All right, so let's see how close that is. So let's go to Desmos. And type in y equals x cubed minus 3x squared. Okay, looks about right. So let's double check. So right, 0, 0, that's our local maximum, local minimum. The 0.12 should be where it changes in cavity. Yeah, right there. Excellent. Okay, and look at the long-term behavior. Of course, it goes to infinity on this side, goes to negative infinity on this side. Yeah, that's it. Now, once again, you may wonder why we spent all that time if we can just simply graph it. And these days we can do that. Of course, remember they could do this in the past, but also these are good skills to better understand how we can use algebra and calculus skills to help us find these answers. Okay, let's do another one of these. And I'm just going to start right here. Let's do one a little bit different characteristics. Number 2, this time our f of x is going to be 3x over x squared minus 1. Okay. Now, once again, we're not putting any restrictions on the domain. It could potentially be all real numbers. But one thing we do have to know and realize is, remember, think about this. What values of x will make our denominator 0? Okay. So what can we square? Basically, what can we square to get x equals 1? Let's go ahead and do that part. This is kind of the part about finding asymptotes and everything. Let's go ahead and do that. Some of these steps, the order is not that important. Okay. The question is, what will make the denominator 0? Okay, so the best way to do that, just set the denominator equal to 0 and solve. X squared minus 1 is equal to 0. Add 1 to both sides. X squared is equal to 1. And of course, that's going to be x squared equals plus or minus the square root of 1, or just plus or minus 1. Okay, so we're going to have vertical asymptotes at x equals 1, x equals negative 1. So keep that in mind. Okay, we graph it. So x can't be that. All right. But other than that, there are no restrictions on the domain. Okay, and if there were, if we said like maybe this function only goes from -5 to 5 or something like that, then you also want to find the values of the function at the endpoints. Okay, so let's go ahead and find the derivative, both derivatives. Now this one, we'll have to use either the quotient rule or another rule. I'm actually just going to use the quotient rule. Okay, once again, I know it's a bit of a pain, but of course, you can always, this one you don't have to memorize. You can use the product rule by just making this as 3x times this quantity x squared minus 1 to the negative first, but I'll just use the quotient rule here to kind of put everything over a common denominator. All right, so the quotient rule says first part, we have the first, remember it's a fraction. Let's do the bottom first. So the bottom is your denominator squared. So this is x squared minus 1 quantity squared. Okay. Then it's the bottom function, x squared minus 1, times the derivative of the numerator, which is derivative of 3x is just 3, minus, and this is why it's the order is important to have a minus, and then it's the numerator function, 3x times the derivative of the denominator, and the derivative of x squared minus 1 is just going to be 2x. Okay, so put that all together. Let's kind of combine that. So I think squeeze that partly in over here. So we're going to leave our denominator as it is. No need to multiply it out. And then if we multiply our numerator out, we're going to have 3x squared minus 3. And this is going to be minus 6x squared. Of course, combine your like terms. And so our first derivative is going to be negative 3x squared minus 3 over squared minus 1 quantity squared. That's our first derivative. Now, this part is a bit of a pain because we actually have to do quotient rule again for our second derivative, but this is good practice in doing that. Okay. So once again, we have a big fraction. And so we have square our denominator, so it's going to be x squared minus 1 squared, and then square that again. Remember, we multiply our exponents together here. That's going to be x minus 1 squared minus 1 quantity to the fourth. And then, once again, the way this works is we have our top function, x squared minus 1 squared times the derivative of our numerator. So it's our base, our denominator times the derivative of our numerator, and that's going to be negative 6x, then minus, then our numerator, which is, I'm just write as negative 3x squared minus 3 for now, and then times the derivative of the denominator. And this actually have to use the chain rule. So 2 times x squared minus 1, and then the derivative of what's on the inside is going to be 2x. Okay, now this is kind of a pain. All right, we'll make it through it. All right, so just kind of take it a step at a time. So our denominator is going to be x squared minus 1 quantity to the fourth power. We're going to leave that as it is. Okay. Now, actually, I'm not going to multiply this through yet. We might be able to simplify something, but let's write this as negative 6x for now times x squared minus 1 quantity squared. Okay. And over here, so hopefully you can follow this all right. So notice both these are negative. If I take a negative out, essentially I'm distributing a negative out. To make a negative out here, make this a positive. And then that would be 3x squared minus 3 times, I'm going to go and combine these. The 2 times 2x is 4x. And then times x squared minus 1. Okay. Now, oh wait, this should be x squared plus 1. My mistake. X squared plus 1 right there. Okay, yeah, be careful with your signs. Okay. Now, there's a reason I did some of that, because, once again, this part's kind of a pain. All right, so just take it a step at a time. Now, the reason I'm doing this, instead of multiplying everything through, is you notice I have an x squared minus 1 here and also here. So it'd be easier to factor that out, factor out an x squared minus 1 out of the front. And so if I take an x squared minus 1 out of both, what I have, I always put brackets here to kind of, instead of using so many parentheses. If I take one out, I have what's left here, negative 6x times x squared minus 1. Okay. And then here, I've taken this out. This is now gone. And then let's go ahead and distribute this. So I have plus 3x squared times 4x is 12x cubed. And then plus 12x. And then I have x squared minus 1 to the fourth. And hopefully you can see what will happen here is I can actually cancel out one of these. All right. And so It's going to make that a 3, so that makes things a little bit simpler. Okay, now I need to distribute this right here. So I'll distribute that. I have negative 6x cubed. Make my 3 look a bit better. No, that's not much better. There we go. 6x cubed plus 6x, then plus 12x cubed plus 12x. And of course, we're going to combine like terms as we can. Down here, I have x squared minus 1 cubed. Okay. Now, once again, combine our like terms. And so if we combine our x squared terms, that's going to be negative 6x cubed and 12x cubed is going to be 6x cubed. I'll cancel those out as I get them. Then combine my x terms. That's going to be 6x and 12x plus 18x over squared minus 1 cubed. Okay, so this is our second derivative. Once again, I know that was a pain, but made it through it. Okay, now let's think about finding our critical values. Okay, so find the critical values. All right, so set our first derivative equal to 0. Let's go back and get our first derivative. Okay, negative 3x squared minus 3 over our denominator. Over x squared minus 1 squared is equal to 0. Okay, now remember our denominator can't be 0. Okay, so the only thing to make this 0 is our numerator. Okay, so now I just have to set our numerator equal to 0. And so that's going to be negative 3x squared minus 3 is 0. All right, add 3 to both sides. Negative 3x squared is equal to 3. Divide both sides by negative 3. Now we have x squared equals negative 1. Okay, now once again, if you try to solve that the usual way, it'd be plus or minus the square root of negative 1. But remember, that's not real, that's imaginary. Okay, now it's still negative plus or minus square root of negative 1 is still a solution to this equation, but it's not real. So what that means, if that happens, it means there are no real critical values, or no critical values. Okay, so that's kind of interesting. So actually no critical values at all. So nothing is going to make the derivative equal to 0. Okay, so that can happen sometimes. Some of these are going to make our life a little bit easier as well. Okay, so let's think about what's next. So actually, since there's no critical values, then let's also think about, let's find possible inflection points. Okay, let's find possible inflection points. We're saying possible because we want to find out what makes a second derivative 0, but it may not be a guarantee it's an inflection point. Okay, so this is 6x cubed plus 18x over x squared minus 1. So that's going to be 6x cubed plus 18x over x squared minus 1 cubed is equal to 0. Once again, for the same reason, our denominator can't be 0. We just have to set the numerator equal to 0. And so it's going to be 6x cubed plus 18x is equal to 0. Okay, now let's factor this. Like you have to factor this. So take an x out and also a 6x out. And if we take that out, what we're left with is just x squared plus 3. Okay, and set each one equal to 0. And so 6x equal to 0. And x squared plus 3 is equal to 0. So over here, clearly x is 0. And then in this case, x squared equals negative 3. And so x be plus or minus square root of negative 3. And once again, these would give us no, this is not real, the imaginary numbers. So this one, just x equals 0, is a possible inflection point. Okay, it could be an inflection point, just that one. Okay, so no critical values, but one possible inflection point. Okay, now, in a case like this, we still don't know where a function is increasing or decreasing. So actually what we're going to do then is actually use, actually I probably need to, I actually need more space. So give me a second. So what we're going to do, that's more than enough. So we have to think about this is, since we don't have any critical values to help us find where it's increasing or decreasing, a function also change from increasing and decreasing around a vertical asymptote. We know of a couple of those, okay? So find, I'll just say where is increasing or decreasing, okay? We're going to use our asymptotes. Okay, and so remember we have asymptotes, vertical asymptotes. So I was making the dotted line since they're our asymptotes at x equals -1 and x equals 1. Okay, so let's think about the sign. So remember our first derivative is -3x squared minus 3 over x minus squared minus 1 squared. Okay, that's f prime of x. Now, that one's a bit of a pain to use. So actually what we're going to do is actually use Desmos to help us out with that. Okay, so we just need to plug in, almost going to need to plug in values on either side. Okay, so here we'll use 0 in the middle. We'll just use -2 and +2. Okay, now what I'm going to do then is let's just use Desmos to help us out. Let's go back here. Let's turn that off. But what I'm going to do is actually plug in my derivative. So I need parentheses here. So -3x, well, what I said it was. -3x squared minus 3. Okay, -3x squared minus 3. Divided by x squared minus 1. Okay, now, purpose of this, let's see if I can actually find -2. Okay, yeah, there we go. So the reason I'm doing this, if you notice right here, plugged in at -2 is equal to -5. The main thing, though, we don't even care about that exact value. We just know that basically here it's negative. You notice, so at -2, the result is negative. Okay, so here it's negative. Okay, I plug in 0. Let's go back to Desmos. At 0, okay, it's positive. Okay, and also then at +2, it's also negative. And this one, you notice this one actually is symmetric. We're talking about the side of symmetry. This one actually is symmetric. Right, it's positive at 0, negative again at +2. Okay, and so that means here it's decreasing. It's increasing here, and it's decreasing. Okay, or actually, hang on a second. Did I type that in right? Oops, hang on. Oops, I realized I made a mistake. I probably got those backwards. This should be over x squared minus 1 squared, quantity squared. My apologies for that. Let me fix that. That's probably going to switch everything. But that's okay. That's probably going to flip everything. But that's okay. Yeah. Okay. So, right. Actually, at 2 and at -2, it's still symmetric. Doesn't change anything. Well, basically, as you can see, everything is negative. Okay. So actually, our no concavity changes. Everything is negative. Everything is decreasing. So actually, this is also negative here. It's actually is decreasing everywhere. And hopefully it kind of makes some sense because we didn't have any real critical values. So it's decreasing everywhere. Okay. Now let's also think about our possible inflection point. Okay. Now here I'll just say find concavity. And where it's concave up or concave down. Let's figure that out. So we're going to use our possible inflection point. Let's underline this here. All right. So our second derivative was this. We have a possible inflection point at 0. So this 6x cubed plus 18x over that. So here we had at x equals 0, and our derivative f double prime of x equals 6x cubed plus 18x over x squared minus 1 quantity cubed. And once again, make sure that's right. All right, so the same thing, we just need to pick values over here. Now, one thing after what you pick is we have asymptote. We can't pick 1 or -1 because those are asymptotes. We'll just pick, say, -2 and +2. And I'm going to do the same thing. I'm going to plug this in, and that's going to be helpful instead of trying to, of course, if you have your calculator, you can also just plug that in values, any of those test values in. But let's also just plug it into Desmos and see what we get. All right, so same way, put parentheses, 6x squared plus 18x 6x cubed plus 18x. 6x cubed plus 18x. And then this then is divided by x squared minus 1 to the third. Okay. Now, right. So that's correct. So what does this tell us? Well, remember, just look where it's positive or negative. So on this side of 0, zoom in a bit. So if we're on this side of 0, on the left side of 0, actually, well, I should back up. So also our inflection, let me just change this. Because actually our inflection points, we can also, our asymptotes, the concavity can also change around asymptotes as well. So I forgot to mention that. So let's do that. Okay, here's x equals 0, and then our asymptotes. X equals -1, x equals 1. Okay. Let's see what happens on here. So here, let's also just pick some values like here. This one's again -2. This picks just say -1/2 or -0.5, positive 0.5, and then also 2. Okay. Now let's see what happens at those points. I was going to apologize. This one's kind of dragging out. This is taking a while, but still, this hopefully you appreciate why you have calculators when you do these things. All right. So let's start over here. If you're at -2, then obviously our second derivative is negative. Okay. So this is, I was going to talk about the sine of f double prime of x. Over here, it's negative. Okay. Now, if you're between -1 and 0, believe that was positive. Let's see. Yeah, so between -1 and 0. And also we can put in our asymptotes that might help us to make some sense of this. X equals -1 and x equals 1. All right. So if you're between -1 and 0, it's actually positive. Okay. And then if you're between 0 and +1, it's negative again. Those do. All right. So between 0 and 1, it's negative, and then also at 2, beyond that, it's positive. So it goes negative, positive from here. Negative, positive. Okay. Now, so what that means, what that tells us, is that right here, it's negative, so it's concave down here, concave up. Over here, once again, concave down and concave up. Okay. Right. So actually, what this tells us then, x equals what was that, 0, is an inflection point. Okay. And also our concavity changes at our asymptotes. Okay. We're almost done with this and got a few more things to do. So let's think about a few more things. Think about our intercepts. Okay. Of course, the intercept, you have to solve what's going to our function. Let's look back at our function, 3x over x squared minus 1. Actually, I don't need the parentheses, just x squared minus 1. So 3x over x squared minus 1. Okay. Now, the y-intercept is the easiest one to find. Plug in 0. So f of 0 is going to be just 0. Okay. Just plug in 0 makes the whole thing 0. All right. Then the x-intercept, I'll put as plural. Of course, it could be plural. We're going to set 3x over x squared minus 1 is equal to 0. And solve that. And once again, our denominator can't be 0. So basically, we just have to find out what makes 3x equal to 0. Of course, that's going to be at 0. So x equals 0. So our y-intercept is 0, 0. And also x-intercept is also 0, 0. Okay. Now, one more thing. Let's think about our long-term behavior. Or let's think about, of course, we know about asymptotes. Think about far from 0. Okay. Now, if you notice, once again, our function, let's write it one more time. F of x is equal to 3x over x squared minus 1. So if you notice, the degree of the denominator, or the degree is the highest power, the degree of the denominator is greater than the degree of the numerator. I'm just going to abbreviate that. So to make sure you can follow my abbreviations here. So denom for denominator, num for numerator. The degree of the denominator, which is squared, which is 2, is bigger than the degree of the denominator, which is 1. So anytime that happens, what that means then is basically go far from 0, this goes toward 0. Okay? So what that means in the limit is x goes to infinity of f of x is the same as the limit as x goes to negative infinity of f of x, which is actually to 0. All right, let's see if we can pull this together and do like a very basic graph. All right, I know we have vertical asymptotes right here, x equals 1 and x equals -1. Okay, I also know our function approaches our asymptotes depending on which way we're going. All right. Now we know we have an inflection point and a y-intercept, x-intercept, and inflection point at 0, 0. And actually, yeah, x equals 0, so the inflection point is 0, 0. We plug in that. All right. So that point's important, 0, 0. Okay. Now, notice a few other things we have. Okay, so we said basically the function is decreasing everywhere. Okay, and think about our concavity. So over here, our concavity, go back to our concavity. Concavity was down over here. So this side of -1 concavity was concave down, all right? And we know it's got to follow the asymptote. So it looks something like this. So far away from 0, it goes to 0. And remember, there's no x-intercept over here, so it stays below the x-axis. You know, it's going to follow the asymptote. It's concave down. It looks something like that. Okay. Now let's do this side over here. That's probably the easiest. It's going to be kind of a similar image. All right. So over there, I believe it's concave up. Yeah, concave up from on the right side of 1. Okay. And also, we know it's got to go towards 0, and it's no intercept over here, so it's going to be entirely above the x-axis. Concave up looks like this. Okay. Now, we know between -1 and 0, I believe it was concave down. Let's see. Yeah, no, concave up, rather. And then concave down the other side. This is an inflection point. We know it's got to follow this, so if it's concave up, it means it's got to go up toward the asymptote. It's also decreasing everywhere. And then it's concave down here. And to follow that asymptote looks something like that. Okay. Now, once again, let's graph it on Desmos, see how we did. I believe we'll be pretty close. So I know this one's also kind of a pain, just a lot of work to do with the derivatives. Let's get rid of all these. Let's come right here and type it. So this is 3x divided by x squared minus 1. Yeah, that looks about right. And also, let's put in our asymptotes. Let's actually turn those back on. Okay, right. As we said, inflection point right here, decreasing everywhere. It's concave down here, concave up in this part, concave down, concave up, approaches. We zoom out, it approaches infinity. It goes to 0 as it goes to infinity. Yeah, so that looks correct. Okay, so those two, especially the last one, took a while, but hopefully get the idea. So that's how we can actually use calculus techniques and derivatives and also algebra techniques you learned before to actually graph functions. And then, of course, you can check them. Now, once again, in real life, you're not going to do this very often, but still, it's a good understanding of how these things work and basically what you can do with calculus and algebra skills. Thank you. Have a good day.